as we get started today, I want to start by just telling you, if you feel a little lost at the end of the lesson, that's normal for this. This is a 2-day concept. Today, I confuse you. I try my best not to, but I confuse you. Tomorrow, as you just stick with me, don't give up, don't panic. Tomorrow it starts to click. It's kind of like, Audrey, as you help me in PE, the first day we talk about bumping a volleyball, it looks bad. And then the second day we bump the volleyball, it's like, oh, they had a day to figure it out and think about it. And it starts to look better. And then we put them in games and they forget everything I taught them. But anyway, but sometimes it just takes that second day. So if today clicks for you, that is fantastic. If it doesn't, that's okay. Okay, we have tomorrow, we're just going to keep working on more of the same. So when we get ahead to solving networks here in a little bit, don't panic on me, all right? Just keep plugging away. It'll click for you, unless, of course, you just check out and say, I give up. Don't do that, okay, is what I'm saying. Let's review some things before we get into the networks, the new material. We've been talking about DC circuits specifically. DC circuit has 3 parts. Michael?
Yeah, it has the source.
Which is generally a?
Battery.
Battery, good.
The wire.
The wire that carries the current.
And then the resistors.
And then the resistors are the loads, right? And the current only flows in that one direction. Again, we talk about conventional current. We're going to assume it travels from positive to negative, even though it doesn't. And so we said that for DC circuits, there's 2 ways in which we can arrange loads or resistances. We could either put them in series or we can put them in parallel. Kind of describe to me what the current does when it goes through a series circuit.
It starts from the battery, and then it travels to one resistor, and then it goes around to another one, and then to another one, and then back to the battery.
Good. It goes through one resistor, then the next, then the next, then the next, then the next. However many there are, it just keeps going through one after another. The term is in succession. It just goes through them in order, one at a time is the key. It can't pass through multiple at once. It passes through them one at a time in order until it gets back to the battery. How would we maybe describe what the current does in a parallel circuit, as opposed to what she described for a series circuit? By the way, the t-shirt, gift of the senior class, apparently they think I sometimes go, okay, because a lot of times I go off on a tangent. The tangents are not always recorded, by the way, on YouTube, so sometimes we'll go off on the tangent and we'll get a late start, or we'll end early so we can go off on a tangent, or sometimes I have to clip them out, but anyway. I digress, so thank you, seniors, for a t-shirt that I was supposed to wear yesterday. Anyway, back to parallel circuit. What goes on there? How could you describe maybe the layout or the look of it? Or more, right? We often will use 3, but it could be 2, it could be 3. As long as if the current goes through them at the same time, that's the key, right? The current goes through them at the same time, because unlike the series circuit where there's only one pathway to follow, parallel provides more than one pathway. There's multiple pathways, and that's how the current can go through multiple places at once. How do we find the total or equivalent resistance for a series circuit, Michael?
Add them all together.
Add all the resistances together. What about for a parallel circuit?
You add the reciprocals.
And then, don't forget to take the reciprocal at the end, right? Thinking back to last test with the 1 over F thing. All right, so anyway, don't forget the reciprocal at the end. What is true about the current, because it goes through one resistance and the next and the next and the next, because there's only one pathway to follow, what is true of the current in a series circuit? What's true about the current that goes through each of the resistances? It's constant. But in a parallel circuit, we said that the current goes through all of the resistances at once. There's multiple pathways for the current to follow, and because that's true, what is true of the current in a parallel circuit?
It's lower. It varies.
It varies depending on
The number of pathways.
the resistance in each pathway, right? It takes the path of least resistance, we'll get more of the current, less of the current where there's more resistance. What happens with the voltage? And I said, think of voltage as what, Kendall? It's not a technical definition, but it's a good way to think of it. Voltage can be thought of as anyone?
Push.
The push that pushes the current through. We've got these delocalized electrons. They're there. They just need something to start them moving. And the voltage is what gives that push. What's true of the voltage in a series circuit, Kendall?
It varies.
The voltage that's used up, again, after you've pushed on something, you get tired, right? Bench press, ever, right? So when you're benching, right, you start off, you're fresh, you're full of energy, and ever done a burnout? Where you start with a lot of weight and you go to less weight, maybe do 10 reps of each, and by the end you're struggling to lift the bar. And it's not that you're not capable of lifting the bar, but your muscles are tired. You have expended energy, and in a similar way, voltage got used up pushing current through this resistor. And then more voltage gets used here, and more voltage here, and more voltage here. We refer to the used up voltage as what, Michael? You don't like it, but that's what it's called. You complained about this the other day.
IR drop.
The IR drop. You did it off camera, but you're like, why do they call it IR drop? I don't know. But IR drop, the voltage drop. There's voltage that's used up. What's true of the voltage that's used up in a series circuit?
Gonna go down.
It is going to continually drop as it goes around, but I said to remember for a series circuit, voltage
Oh,
varies by resistor. The bigger the resistance, the more voltage gets used up. The bigger the drop in voltage or electrical potential difference as it goes around. Whereas in a parallel circuit, Audrey, I said to remember what about the voltage? It's constant because all the voltage gets used at one time, so it's the same voltage across each resistance. Different voltage used on the resistors of a series circuit. And of course, yesterday we began talking about circuits that are a little bit more complex, that have both series and parallel in them. Class, we call these networks. And we began looking yesterday just at finding equivalent resistance of a network. If you would, on your paper, go ahead and draw this network. We'll start with our battery. We'll have the current go out from the battery and pass through a single 4 ohm resistance. The current is then going to split two ways. The first way, there will be just a couple of resistances. And let's suppose they are 3 ohms and 1 ohm. The other direction, the current's going to go through 1, 2, 3 resistances of 2 ohms, 3 ohms, and 6 ohms. Before the current through this branch or this pathway meets up with the current from this branch or this pathway, heads back toward the battery, passes through one more resistance of 5 ohms before reaching the battery again. Imperfectly drawn, should be nice right angles. I'm going to slant that line up there to get it. Maybe you'll have better luck than I did as you use that nice blue lined paper. I say that, and my notes are on blue lined paper. I still didn't get them that great, even on the blue lined paper. Nice thing is, quizzes and tests will be computer generated, so they'll look great. But here they're Nadasky's hand generated, and so they don't look great. Before we get into solving the network, I just want to review how to find the equivalent resistance, because that is always your first step with any circuit, whether it's series circuit, parallel circuit, or a complex network. To find equivalent resistance for a network, I said start class by simplifying any series circuits. Do we see any series? Where?
3 and 1.
The 3 and the 1 are obviously just in series together, class. What is the resistance right there in this little branch?
4.
There are 4 ohms of resistance in that little branch. Are there any other series?
2, 3, 6.
Do you see that the 2, 3, and 6 are all in series together? They're not lined up with each other on the schematic, but they're all in series within that branch. Do we see that? So this branch of the parallel arrangement has how much equivalent resistance? 11 ohms. Are there any other simple series? No. All right, if we were to redraw this, and you don't necessarily have to redraw, but if we were to redraw it, we would have a 4 ohm resistance here. We'd have a pathway with 4 ohms here, a pathway with 11 ohms here. These two reconnect and pass through the 5 ohm here. You see what we kind of simplified? I usually do it by circling and writing off to the side. So once we've simplified simple series, and we've done all that there was to do there, now we go to simple parallel. Are there any simple parallel? What do we have?
4.
The 4 and 11. If I'm going back to the original schematic, I could say all of that. is simple parallel. And what is that going to be? We definitely need calculators for this.
2.93 repeating.
Okay, so we end up with 0.3409, where the 09 is going to repeat over and over again. We may want to use a memory for that. We've got 3 memories in it, yes, sir?
I think we all got 2.93.
We've got 2.93. Okay, let me try again. 4 reciprocal plus 11 reciprocal equals, take the reciprocal at the end, just like I said, right, Kendall? Let's try 2.93 repeating, which is even easier to plug in. I was just saying if you were paying. No, I just screwed up. All right, so we got 2.93 ohms. That's all of this. Again, if we're doing it on a simplified schematic, we could write it this way. Now we go back to any
Series.
simple series. Do I have simple series now?
Mm-hmm.
Yes, in fact, they're all a simple series. 4, the equivalent of 2.93 repeating, and 5. And we add those together to get class.
11.93.
Now, as far as the work later on is concerned, we may have to round this off and say we've got about 12 ohms, but for any math we do, we would use the 11.93 repeating in calculation. All right, questions on that equivalent resistance? Let me give you one of these to try on your own. From the battery, current goes out, passes through a single ohm resistance. Goes down through 2 ohms and 3 ohms, or could split off, go through a 4 ohm resistance, and then split again into 5 ohms and 6 ohms. Current reconnects from here, reconnects to here, passes through a 7 ohm resistance before reaching the battery. I assume we started by identifying that these two resistors are simply 5 ohms, simple series with each other, correct? Then we should have identified that these two, not this one as well, because this 4 ohm separates this branch from those other two, but these two have nothing between them. So these two are simple parallel, and when we use reciprocals, and don't forget to take the reciprocal at the end, we get 2.72 repeating ohms for the simple parallel. Still so far so good? Not so far so good. What did you have?
I included that.
You included the 5 here. Does it make sense now that these are separated from this because of that little 4 ohm doohickey? At this point now, if we were to redraw the schematic, I'd have a resistor here, a resistor here, a resistor here. I'd have a resistor here and a resistor here. Do you see that these two, this one and this one, are now simple series with each other? So collectively, this class would become 6.72 repeating ohms. Do you see that all of this 6.72 would now be parallel to the 5 right here? So we have a 5 right here, and all of this stuff becomes a 6.72. These two guys are now in parallel to each other. Now it's getting a little dicey here from not redrawing the schematic, but 5 and 6.72 are in parallel, so we'll take the reciprocal of the 6.72 repeating, plus the reciprocal of 5, take the reciprocal of that, and all of this becomes 2.868, and now we're beginning to question our life choices and think maybe we should have tried a redrawing of the schematic. All of that becomes 2.868, or maybe you lightly did it in pencil so you could erase some things as you went. But the key is the current goes through a 1, what becomes 2.868, and then through 7. And these 3 resistances are now in series. So I add them together, and I get 10.868 blah, blah, blah ohms of equivalent resistance. Did we end up with that answer? Michael did, Kendall did, and Audrey, you found your mistake earlier. Does it make sense now on that? All right, questions? All right, the good news is this is a little bit more complex than what we'll usually do, but just like in athletics, you train harder than you play, right? You train yourself, your body to go further than what you have to do in a game. We're kind of pushing you a little further than you'd have to on quizzes and test questions. All right, so now then, let's get to finishing solving networks. Let's finish up solving networks now. And I said in the notes, if you look back at your notes from yesterday, step number 1 was we had to figure your equivalent resistance by doing 3 things. First, simplify any simple series, then simplify any simple parallel. And then just go back and forth, series, parallel, series, parallel, series, parallel, until eventually you have equivalent resistance. That's where we've stopped. What we want to be able to do next is find the current through the circuit, the IR drop at each resistance, the current through each resistance. So let's set up something that maybe is a little bit more like what you'd see on quizzes and tests. In fact, this one's kind of a straightforward one here. Let's start with a 12-volt battery. Heretofore, I have networks. I haven't given you the voltage of the battery because we haven't needed it. All we've been finding is equivalent resistance. But to solve, we need to know how much voltage the battery can put out. Let's have the current pass through a 4 ohm resistance. From there, the current will split 2 pathways. One has 6 ohms of resistance, the other 3 ohms of resistance. The current can then reconnect from these 2 pathways to go through a 2 ohm resistance and back to the battery. I'm not a perfectionist or anything. All right, 12 volts, 4 ohms, split to 6 and 3, and then back through 2 before returning to the battery. As always, we find equivalent resistance first. At your seats. It shouldn't take more than about a minute. Go ahead and find the equivalent resistance. one of the things you'll want to do is what I was showing a moment ago on the schematic. You'll want to go ahead and label for this parallel set, so to speak, what the equivalent resistance was, and what did we get for the equivalent resistance here, class?
2 ohms.
2 ohms. So we got 2 ohms for the parallel. So total resistance, class, is 8 ohms of equivalent resistance. Once we've calculated equivalent resistance, that's what we practiced yesterday, that's what we've practiced so far this lesson, then we need to find the total current, the total output, if you will. We've got a lot of free electrons, but there's 8 ohms of resistance keeping the electrons from simply flowing through the circuit. But we've got 12 volts we can use to push them. 12 volts pushing through 8 ohms gives how much current? We're kind of ignoring sig figs at the moment, by the way. 1.5 amps comes out evenly. So just as the resistance came out evenly, the current has so far has come out evenly as well. 1.5 amps of current. Now what that means is that 1.5 amps of current gets pushed through the battery. It's flowing through the wires. 1.5 amps goes right here because there's nowhere else to go. But then what does the 1.5 amps do, class? It splits. Some of it here, some of it goes there. We're going to have to figure out how much of the 1.5 amps goes here, how much ends up there. Does that make sense? But then the current that went through here comes back this way, and the current that flowed through there comes back that way, and they rejoin so that when they get to the 2 ohm resistance, how much current is going to go across the 2 ohm resistance, class? 1.5 amps, right? There was no other pathway. They had, all 1.5 amps had to go across the 4 ohm resistance. Does that make sense? And later on, the 2 ohm resistance was the only path back to the battery. 1.5 amps has to go across the 2 ohms. But 1.5 amps doesn't have to go here or here necessarily. It splits. Some goes each way. So when we set up our table, where we list out our resistances, 4 ohms, 6 ohms, 3 ohms, 2 ohms, when we list the current that goes through each, when we find the IR drop or voltage drop at each, when we go to set up that chart or that table, the simple series resistors, and you say, well, 4 and 2 aren't actually in series with each other. I know they're not, but by simple series meaning that's the only pathway at the time. The easy ones, the solo pathway ones, you know the current that leaves the battery is the current through those resistances. The total current, the current that gets pushed by the battery, is the current through any simple series resistors, meaning resistors that have nothing whatsoever to do with parallelism. Okay? Well, if I know R and I know I can get IR. How do I get IR if I know R and I? Multiply, just like IR suggests. And so 4 times 1.5 class, 6 volts. And down at the bottom, 2 ohms, 1.5 amps. IR would be 3 volts. That make sense? Let the easy stuff be easy, and the simple series resistors are the easy ones. Because once you know total current, you know the current through those ones at least. What I like to do on my little chart is I like to group these together with a little bracket. That helps me remember that collectively, those two are working together. When we approach parallel, here's how we're going to approach it. I approach it like the Russian stacking dolls. You know what I'm talking about, right? You've got the whole big stacking doll. You open it up, there's a smaller doll. Open it up, there's a smaller doll. When it comes to parallel, here's my approach. The whole big parallel. Then I take a look at each branch of the parallel. And then I say, okay, now within each branch, there could be multiple resistors. Then I look at each resistor in the branch. So I'm going to start by looking at the whole parallel. The whole parallel, all of this class, has 2 ohms of resistance, correct? And even though the 1.5 amps is going to split, some here, some there, the whole thing is getting 1.5 amps, correct? So if I know the current of the whole thing, and I know the resistance of the whole thing, I can therefore find the voltage of the whole thing. Does that make sense? What is the voltage of the entire parallel set? IR, 3 volts. The other way we could have figured this out, and it's not going to be something I want you to do because more complicated circuits won't work out this way, but remember how many volts I had to start with? 6 volts got used up here, 3 volts got used up here. How much voltage is left? 3 volts. There's the last 3 volts. They get used up at this whole thing. All right, so let me say it again. You may want to jot this down. If you know the resistance of the whole parallel set and the current of the whole parallel set, you can find the voltage used by the whole parallel set. Notice my focus is on the whole parallel set here. I know the resistance, I have to. In order to find equivalent resistance earlier, I had to find it. I know the current of the whole parallel set. It's got to be whatever the total the current is, because it's got to go across that set. It's going to split while it does, but the whole set does get 1.5 amps still. So I can find the voltage of the whole parallel set. Now here's the key. This is voltage of the whole set. The voltage that the whole set gets, remember in a parallel circuit, voltage is constant. Whatever the voltage is that the set uses, that's the voltage in each branch. Each branch gets 3 volts. Because in a parallel circuit, voltage is constant. So once you know the voltage of the whole set, this is the voltage in each branch. Does that make sense? That set uses 3 volts. That means each branch gets 3 volts to push through. I also know the resistance in each branch. This branch has how much resistance, class? 6 ohms. This branch has how much resistance? 3 ohms. By the way, even if there were multiple resistors in here, I could still figure out the resistance in the branch, right? So I know 3 volts pushes through this branch and encounters 6 ohms of resistance. 3 volts pushes through this branch and encounters 3 ohms of resistance. If I know V and I know R, I can find I. How do I find I given V and R? V over R, the same way we found this here, right? I've got 3 volts and it's got to push through 6 ohms. How much current do I get? Half an amp. I've got 3 volts and 3 ohms. How much current do I get in this branch? 1 amp. We use the voltage in each branch. Here's the next thing, little segment. Do you notice that the last time I said 3 things about parallel set? You know the resistance of the whole parallel set, you know the current of the whole parallel set, so you know the voltage of the whole parallel set. That becomes the voltage in each branch. If you know the voltage in each branch and the resistance in each branch, you know how much current goes into each branch. Once the current goes into the branch, it's got to go across any resistors in the branch, right? So once the current has chosen, so to speak, half an amp, we're going to go here. And so half an amp goes here. It's like Kendall. Half an amp goes here. You said you'd miss the short jokes. Half an amp. I'm writing it now. Audrey wrote that for me. All right, so half an amp, once it's chosen, so to speak, to go in here, it has no other place to go, correct? Once it goes into the branch, this is the only pathway it can take to get back here. So half an amp must go right here across the 6 ohm resistor. Once a full amp has chosen, so to speak, to go into this branch, it has to hit every resistor in its way. Well, there's only a 3 ohm resistor, but that's where the 1 amp goes. Does that make sense? So once you know the voltage in each branch and the resistance in each branch, you can find the current in each branch. And if you know the current in each branch, that is the current through each resistor in the branch. Now, it could get dicey if the parallel split again into another parallel. We're going to let that be for college. It's really not that. You could probably figure it out. You would just have to refigure a new parallel now. But we're going to leave that for college level, okay? This is high school physics. But for our purposes, once the current goes into the branch, it has to hit every resistance along its way. Once current goes into its branch, it hits every resistance in its way. And now that I know the resistance, the current through each resistor, I have R, I have I can get IR. What's IR? And interestingly, you notice it's 3 volts for both of them. Because in a parallel circuit, voltage is constant, current varies. In series circuit, current is constant, voltage varies. Does that make sense? Not asking could you do it on your own, because I know you couldn't yet, but does it make sense the logic used here? All right, let's do another one together. Let's, this time, scale down to a 9-volt battery. And let's have the current go through a single ohm resistor before splitting. Split into a 2 ohm resistance and a 4 ohm resistance this way, or it could go this route and go through 3 ohms of resistance. The current then reconnects and back to the battery. At your seats, find equivalent resistance. Should have identified that this branch has 6 ohms. This branch, of course, just has 3. Differentiate with some yellow chalk here. All of this, then, has how many ohms of resistance, class? 6 and 3 in parallel? 2 ohms, using the reciprocals. And then I've got an ohm and 2 ohms. Gives me the equivalent resistance, 3 ohms of equivalent resistance. All right, Kendall's good to go. Michael nodding. Audrey, yes. All right, once we know that, we can find the total current that flows through this circuit. And how much current goes through this thing. Class?
3 amps.
3 amps. You simply divide the 9 volts by the 3 ohms that the 9 volts have to push through to get 3 amps of current that flows through the circuit, through the network. So far, so good. Now we make the table. We list our equivalent resistance, or we list, our resistors. We find the current through each and the IR drop at each. Resistors are 1 ohm, 2 ohms, 4 ohms, 3 ohms. I'm going to put the 2 and 4 together, and I'm going to list that paired up with the 3. So I kind of use those little markings on my table. You don't have to, okay? It just helps me to see, okay, these 2 are working together. This one's working with those 2. Just, it's a mental thing for me, I guess. If it's a help to you, use it. If it's not, don't bother. The advantage I see in bracketing things that work in parallel is if it ain't got a bracket touching it in any way, it's simple series. It's straightforward. It is only course for current. 3 amps leaves the battery. 3 amps, class, has to go where? Through the 1 ohm. Now 3 amps doesn't have to go through all the others because there's options, but there are no options at this point yet. There's still all 3 amps. And if 3 amps through 1 ohm, it uses 3 volts. Let the simple series be easy. Now we come to the less easy part. And I said we're going to start, when it comes to the parallelness, we're going to start by focusing on the whole parallel set. The whole parallel set has 2 ohms of resistance. And the whole parallel set gets how much current? 3 amps. Now, it splits which way it goes in the parallel, but the whole parallel does get the same 3 amps, correct? And if I know that there are 3 amps going through 2 ohms, that's going to use up how much voltage? 6 volts. This is the voltage that the whole parallel uses. And if that's the voltage of the whole parallel, because voltage is constant, that is the voltage through each branch. Go from the whole parallel to the branch. I know each branch uses 6 volts. And I use those little arrow notations to show 6 volts going down to each of them. Now this particular branch class is going to provide how much of a fight to these 6 volts? 6 ohms of resistance, where this branch only resists with 3 ohms. If I have 6 volts pushing through 6 ohms, how much current can go through this branch, class? 1 amp can go into that branch. The other branch also has 6 volts, but it only encounters 3 ohms of resistance. So therefore, how much current can go through that branch? 2 amps. Do you see that there are 3 amps going through that parallel? 1 of the amps goes here, 2 of the amps goes there. Is it making sense? So I looked first at the whole parallel set. 3 amps, 2 ohms, 6 volts. That becomes the voltage through each branch. 6 volts, 6 ohms, 3 ohms, 1 amp, 2 amps. Now here's the deal. I've gone from the whole parallel set to each branch. Now I need to look at each resistance in the branch. Once 1 amp has made up its mind to go through this branch, 1 amp has to cross what? 2 ohms and then 4 ohms. Each of them get the same 1 amp of current. Start with the parallel set to get the voltage. Look at each branch to get the current. That current has to go through the resistances. So that means how much current has to go through this resistance, class? 2 amps, because that's how much went into that branch. So therefore there must be 2 amps to go across that resistance. Make sense? Once we've got the R and the I filled in, I just get the IR drop, class. How much voltage gets used at the 2 ohm resistance? 2 volts. How much voltage gets used at the 4 ohm resistance? 4 volts. Notice that's the 6 volts that went into the branch. Use up 2 of the volts, then 4 of the volts, that's all 6 volts for that branch. 3 ohms, 2 amps. How much voltage gets used there? All 6 of the volts that went into the branch, because it was the only resistance in the branch. Of course it's going to use all 6 volts. It's the only resistor in there. And if we notice, 6 volts here, all of this collectively 6 volts, this little guy, 3 volts, there's your 9 volts you started with. Starting to make more sense now that you've seen it a couple times. Let's do another one together. I'm not quite ready to turn you loose yet. All right, let's do eeny, meeny, miny, mo. Let's do this one. I've got 2 more on here. One of them's going to wind up being homework, so let's do this one together. Growl. Okay. Let's have our battery, and let's suppose it's a 6-volt battery. Current goes out, goes up through a 2 ohm resistor, goes over to a 3 ohm resistor, and starts heading back toward the battery. Then it splits. It splits so that there's a 4 ohm resistance here, and there's a, let's see, a 1 ohm resistance and a 5 ohm resistance. By the way, do you see that where I put the 5 ohm resistance here, you realize it would be the exact same if I put the 5 ohm resistance here. Even if they're not directly in line with each other, once the current has split this way, it has to loop all the way through here. Do we see that? Just want to make sure I pointed that out. I'm going to leave it this way. You can leave it the way you have it on your paper. It's fine. But at your seats, go and find the equivalent resistance. We see that these two guys are just 5 ohms, right? Right off the bat. We also see that these two guys here are 6 ohms. Really then, I've got this 4 and 6 that are in parallel together. So I'll take reciprocal 4 plus reciprocal 6, take the reciprocal. How much resistance is in this parallel right here, class? 2.4 ohms. Did we get 2.4 ohms for that whole parallel thing going on over there? Everyone get 2.4? Did not. Okay, try it again. Did you get the 6 for this branch? And 4 and 6 reciprocals? Plug it on the calculator again. Reciprocal 4 plus reciprocal 6 equals, and then don't forget the reciprocal at the end like I did earlier. After cautioning you not to forget the reciprocal at the end. Do you have it now? All right, so we said all of this is 5, all of this is 2.4, so class, what's the equivalent resistance? 7.4 ohms. Now realize, we've got more ohms of resistance than we have voltage to push through. We're not going to get even a whole amp out of this, are we? We're going to have to divide, and we get very little current. What do we wind up with?
.810.
0.810, those 3 digits repeating amps, right? Only 0.810 amps. Store that in the memory of your calculator. 0.810 repeating amps. Less than 1 amp. Let's make our lineup. We've got 2 ohms, then 3 ohms, then 4 ohms, and 1 ohm and 5 ohms. The 1 and 5 work together, and the 4 works with the combined 1 and 5. And we got the chart set up. If it ain't got a bracket, it's easy. The 2 and the 3 don't have brackets. They're easy. How much current goes through both the 2 ohm and 3 ohm resistances, class? The 0.81 amps. Now, I'm going to multiply by the actual memory value, though I don't know that it'll make a whole lot of difference. How much voltage then gets used? What is the IR drop at the 2 ohm resistance? 1.62 volts, 1.6, whatever. Again, kind of ignoring sig figs right now just for the sake of ease. When we get to quizzes and tests, we'll have decimal places and stuff to make sure it's clear. What about for the 3 ohm resistance? 2.4 or 2.43 volts, and the 162s and the 243s repeat, whatever. Okay, there's our voltage so far. Now we get to the brackety stuff. And I said, start by looking at the whole parallel. What do I know about the whole parallel, class? I know there's 2.4 ohms of resistance. What else do I know about the whole parallel?
It has 0.81.
It gets the whole thing gets 0.810 repeating amps. And if I know the resistance of the whole thing, and I know the current through the whole thing, I can find the if I know I and R, I can find V. I can find the voltage that the whole thing uses up. How much current does the whole thing use? 1.945 with the 945 repeating volts. I'm going to go ahead and store that in memory too, just in case I need it. Does that make sense? You know the resistance of the whole thing. We had to find it to get equivalent resistance. I know the current because whatever the current of the battery is, that's the current that does flow across the whole parallel. Splits while it does it, but it all gets there, right? Therefore, I know the voltage of the whole thing. And once you know the voltage of the whole thing, that becomes the voltage through each branch. So now I'm ready to look just at this little branch and that little branch. This little branch has 1.945 volts pushing through it. This branch has 1.945 volts pushing through it. What else do I know about this first branch, class? There's 4 ohms in it. What do I know about this branch?
There's 6.
I've already got it written here, but I'll write it again. There's 6 ohms in it. If I know the resistance of the branch, and I know the voltage in each branch, I can find the current in each branch, correct? That's what I really want to know. I know I've got 0.81 amps, some of it here, some of it there. By the way, more of it here, because it's a little less resistance. So, I have V, I divide by R to get I.
0.486.
This particular branch gets 0.486 blah, blah, blah amps of current. Now, once 0.486 amps has chosen to go this way, all 0.486 amps has to go across the 4 ohm resistance. So the 4 ohm resistance gets 0.486 repeating amps. Well, if it gets 0.486 repeating amps and it's 4 ohms, how much voltage gets used up? 1.945 volts. All the 1.945 volts that went into the branch got used up at that one resistance because there was only one there. Come to the next branch. 1.945 volts, but 6 ohms of resistance. How much current chooses, so to speak, to go into that branch? 0.324 repeating amps. And once 0.324, I was a trifle early there, repeating amps goes into the branch, all 0.324 repeating amps have to go across the 1 ohm and the 5 ohm. Does that make sense? Because they're both in the branch. So both of these get the 0.324 repeating amps. Make sense? If 0.324 repeating amps goes across 1 ohm, how much voltage does that use? 0.324 repeating volts. If 0.324 repeating amps goes across 5 ohms, how much voltage does that use? 1.621 repeating volts. And by the way, you put those together, there's the 1.945 repeating volts we started with. Whole parallel set, I know R, I know I, get V. That's the voltage in each branch. I know voltage, and I know resistance, I get current. If that's the current in the branch, that's the current through all the resistors in the branch. That's the current in the branch, that's the current across the resistors in the branch. Finish the chart. All right, here we go. Here's your homework problem. Copy it down. See how you do. Again, if you don't get it, that's okay. Just do your best. Get it the best you can. We'll go over it tomorrow. We'll practice more tomorrow. I'm going to start you off with a 12-volt battery. Current is going to go across a 4 ohm resistance. Before splitting, the first branch has a 1 ohm resistor and a 3 ohm resistor. The second branch has a 2 ohm resistor and a 6 ohm resistor. These two branches reconnect, and just before they get back to the battery, they encounter another 5 ohm resistor. There's the network for you to solve for homework this evening. Do your best. Tomorrow we'll go over it, we'll practice more of these, and I feel like by the time we're done tomorrow, you should have a pretty good idea of what we're doing if you don't know now. Just out of curiosity, does anyone feel pretty good about this already? Michael does. Audrey and Kendall, a little shaky. Just do your best then, ladies. Okay, don't sweat it. Don't worry about it. Just do your best, and tomorrow I think it'll all start to click for you, all right? Have a wonderful rest of your day. You are dismissed.